Thank you for the introduction, and thanks for the organizers for the invitation to give this series of lecture course together with Arthur César Lebras. And because we are two speakers, we came up with a title which is twice as long as the usual title. So we want to talk about the geometrization of the p-adic local Langmuir correspondence in the case of local analytic representations. But as this theory is still, let's say, in its infancy, we will rather try to explain what the players are supposed to be on the automorphic side, which is the job of Arthur César, and on the Galois side, which is a little bit more of my job. And then we will try to explain, well, some small kind of pieces that might in the future connect these two worlds. So that's a little bit the idea and the program for this lecture course. But let me give you hopefully a little bit of a better idea what this is supposed to be about. By relating it to the picture that Falk and Scholze came up with in the smooth case. So let's start with F over QP, a finite extension, and G over F, a reductive group. Which I maybe assume to be quasi-split. Later on, in order to make my notations lighter, I will stick to GLN anyway, but at least I want to emphasize that there should be a version for a quasi-split group in general. And then Falk and Scholze came up with the following conjecture. And there is a related version of Chin-Men-Ju using slightly different moduli spaces, but which will not have a counterpart on this side of the blackboard, at least as far as I can see. And hence I will stick to the version as formulated by Falk and Scholze, where you want to relate categories of representations. So you take the category of smooth representations of G of F on QL bar vector spaces. So that's the category of smooth representations, and this maybe just means bounded derived category whose cohomology is finally generated as a representation. And this is supposed to fully faithfully embed into the bounded derived category of coherent sheaves on the stack of L parameters, which I maybe just want to call XLG. So that's a stack over QL bar of L parameters for G. Okay, and Falk and Scholze even tell you in some sense to which regard this embedding should fail to be an equivalence of categories by embedding this category into a larger category, which they call D-lis ban G QL bar, such that here you actually obtain an equivalence of categories. And this equivalence of categories even should kind of come with way more additional structures that you can't yet see here that should help you to kind of build the bridge from one side to the other.
And do you have, when you have the equivalence, do you put boundedness on the other side?
Well, I should put compact objects in here, and then the conjecture should be as written. But as I maybe don't even define what this means, I maybe don't want to go into this. I mean, okay, let's put I guess with the same notation that Falk and Scholze use a little omega up here, meaning compact objects, and then it should be like that. Anyway, the aim of this lecture series is to come up with a similar picture. With an analog for p-adic local analytic representations. Okay, and the idea is that you want to get a diagram similar to this one, where here you put some derived category of local analytic representations of this group with values in QP. And here, then there will be lots of question marks in this diagram. There is some kind of corresponding stack of something with the 2L parameters or Galois representations. And then there should be some enlargement which takes a similar shape as in the Falk-Scholze conjecture that you hopefully can relate even better, and where you have more extra structures that actually help you to say something about this question mark errors. So that's the rough picture, yet I guess maybe nothing of what I wrote has a meaning. So I should at least say a little bit. So what I called LSG check here, that's the object of study for this talk. Okay, and that's what I will discuss in detail later. What I wrote down over here, that's the object of study of Arthur César Lebras' talks. Okay, and hence I will not.
Is it important that like the bar over QP is missing? Or
There's no QP, no bar over QP. No, I mean I could have done this rationally as well, not passing to an algebraic closure, but well, then you have to lose a few words about rational structures and so on, and hence in the framework of this conjecture I usually find it easier to work with QL bar coefficients, which you can't here because your object have more of an analytic flavor. Like this stack, for example, is defined over QL, and there would kind of be no serious difficulty of stating such a conjecture over QL. Right. So that's a little bit the program, but I maybe still want to give you at least a bit of an impression what the left-hand side, the representation theoretic side, is about by telling you roughly what local analytic representations are supposed to be. So here, web LA G of F is the category of locally analytic representations of the p-adic Lie group G of F on topological QP vector spaces. Okay, and p-adic Lie group in particular means that this one here is locally, so has charts as a p-adic manifold, which looks like ZP to the something. Okay, so it's locally isomorphic to ZP to the D. And this very feature allows me to define what a local analytic representation is. So that's a notion due to Schneider and Teitelbaum. Okay, and that's the group, and maybe my vector space is called V. And locally analytic just means for each V the orbit maps the orbit map. I fixed my V from G of F to V. And G goes to G times V is locally on such charts like ZP to the D. And given by convergent power series with coefficients in V.
So here V is like a Banach or
Just a second.
What kind of topological vector space you have, like Banach or Frechet? Which kind of condition you have for having a good theory?
I can't hear you.
What is the assumption on the topological vector space to have a theory of analytic functions into it? Is it?
I will be very vague about it and not say anything about it. I will mention in a second that there is a derived variant of this developed by Rodriguez Jacinto and Rodriguez Camargo, where, as you would need it in any kind of derived world that involves topological objects, do this via a solid and condensed formalism. And there, kind of the coefficients could be any solid QP, not algebra, any solid QP vector space.
Why do you restrict to this local analytic one rather than Banach one?
Because it works better for me. Let me finish writing the sentence. It's given by a convergent power series with coefficients in V. And actually, about this, I don't want to say anything more, but I just want to mention that there was a derived variant. I guess I can't put this further up. I'm sorry for this. I'll put it down in a second. There was a derived version of this which would allow you to talk at least about the objects in the upper left corner. And then there was a question why to, in some sense, restrict or pass to local analytic representations in this p-adic picture instead of Banach space representations. Well, one answer is because you can do something about this in the local analytic world, and yet you have no idea what to do down there in the case of Banach space representations. Another thing would be that passing to local analytic representations sometimes allows you to see more internal structural representation, which is also well, quite useful for some things, and maybe giving some example towards the end of the second talk, I could also kind of elaborate a little bit further on that. I hope that's roughly a satisfactory answer, though I don't know who asked. Okay. At least no one seems to complain. All right. So, having tried to set up this roadmap, let me come to the task of my first talk, namely to introduce what these, well, roughly analog of the stack of L parameters is supposed to be. Okay, so these are moduli stacks related to Galois representations. Okay, and for simplicity, I will immediately move to F being QP and to G being GLN. So there's also my dual group G check that appears in the notation up there with just GLN. Okay, and the fundamental object to define these kind of moduli stacks is the Fark-Fontaine curve attached to C together with its Galois action. So let C be the completed algebraic closure of QP, and X Fark-Fontaine, the corresponding Fark-Fontaine curve. So that's the spectrum of the Witt vectors of OC flat. And then you remove this divisor P times Teichmüller of a pseudo-uniformizer of this tilted perfectoid field. So that's the Fark-Fontaine curve over attached to C, which is kind of a curve of a QP, though not finite.
You want the quantum back for views?
Oh, thanks. Divided by phi to the z. Thanks a lot. And since this one here by construction obviously comes equipped with a Galois action, this object here inherits a Galois action. Okay. And what I want to do is I want to consider the following stacks. Stacks on with QP, which are widget analytic spaces over QP. And I maybe want to equip them with état topology. So that saying stack actually makes some sense. And well, since it's a curve, I want to parameterize vector bundles on the curve. But this is a curve which comes with some extra structure, namely the Galois action, and hence I don't just want to parameterize vector bundles, but equivariant vector bundles. Okay, so that's just what I've written down. So let's call this the first stack LS Fark-Fontaine, and now my group is just GLN. So I take some affinoid Adic space spar A, and I map it to, how did I write this? Rank n vector bundles E over spar R times the Fark-Fontaine curve, and I equip them with a continuous lift of the Galois action. So locally, this is isomorphic to some complete tensor product A times structure sheaf. to some power, and on the space wings I have an action of the Galois group, and this I want to lift, so that I have a semi-linear action on my vector bundles, and all the actions involved are continuous, so it actually makes sense to ask whether this is continuous. Okay, so this is the kind of natural object to consider. And that's what I put on that side, well, in the case of GLN.
Is there a reason why you take rigid analytic spaces and not in general analytic spaces?
Whether there's a reason to restrict to rigid analytic spaces. Well, because it's easier for me to work with them. In fact, there should be even more concerns about the test category that you want to put here, which I will maybe discuss a little bit in the second talk. But in some sense, and that should maybe be the perspective of this talk, I want to limit myself to the easiest possible test category that you can write down.
If you want it to be a stack for topology, there is some shiftiness.
Yes, you can prove
this. It's not true for general Hubble pairs, but is so you need something to have a good.
Right. I mean, like one reason why one maybe wants to restrict to some kind of small and easy to control test category is that you indeed want to be able to prove that it is a stack. That's what I've worked down satisfies descent. That's one issue, but kind of there are some other issues with this test category which are a bit annoying, which I maybe will discuss a bit in the next talk. Okay, and then I want to consider the following variants that should maybe help me study this object. Namely, I have a special point on my Fark-Fontaine curve, which is the point infinity. So that's a distinguished point. That my Fark-Fontaine curve provides me just because I started with a field in characteristic 0, and I can remember that C flat is a tilt of C, and it's stable under the Galois action. Okay, and then Fontaine's ring B1 plus is nothing but the complete local ring at this point, and certainly subjects down to C, which is the residue field at this point, and all of these structures come equipped with an action of the absolute Galois group of QP, of course. And maybe I just take a tiny bit of more space and continue down here. In order to study this object that I've wrote down up there, it might be maybe useful to see what happens if I take a vector bundle and I complete it along infinity. Okay, so I want to give a home to kind of writing down what the map E goes to the completion of E along this distinguished point means. And then, of course, you naturally end up writing down a map to the following object, which you again first have to convince yourself that it actually is a stack. So these are finite projective A tensor B1 plus modules of rank n together with a continuous semi-linear Galois action. Modules, I don't know, let's call them M plus Gal QP is acting on M, continuous and semi-linear. Okay, And then you can do something further, namely not just complete, but takes a fiber, and you end up down here. So I'm basically writing down the same thing, but this time I'm working over A tensor C instead of A tensor beta 1 plus. All right, and
So again, I mean, you could have just done the naive thing of just looking at rank n vector bundles over spot A with a Gala action. Are you going to say something at some point about why you do this more fancy thing? Like,
yes, I will.
Okay.
I don't know whether in satisfactory detail, but
maybe just writing down some.
I will write down something. Yeah. But before doing this, I actually want to make two remarks. The first thing is that there exists a variant for G quasi-split reductive instead of GLN, and maybe even for P and G parabolic. So I just want to emphasize that there is no harm of writing down all these objects in greater generality than just for GLN. Okay, and then the second thing I would like to discuss before trying to answer Dustin's question a bit more in detail is I want to discuss the case of GM, or I want to begin discussing the case of GM, which will reappear later respectively in my next talk, so not in Arthur César's talk. So what does this whole picture look like? So the stack for the Fark-Fontaine curve in the case of GM just looks like a certain rigid space T divided by GM, where I take the stack quotient for the trivial GM action. And I should tell you what T is. T, well, as a functor, you can easily write it down. It's the space of continuous characters of QP star with values in varying affinoid algebras. So that's kind of, well, it's functor of points. And I just assure you that it is representable by a rigid space. By writing it out as GM, well, I decompose QP star as usual as P to the Z times ZP star. And then you can easily see that specifying the value of a continuous character on P to the Z just gives you an element of GM. Times the continuous characters of ZP star, and that's something well studied, and you can convince yourself that this is the same thing as the SPIF of the completed group ring of ZP star, and well, which gives you a semi-local formal scheme, and then you take its widget generic fiber. And I guess from writing it out like this, I guess it's also obvious to see what the universal character over this guy is. Okay. And I want to note that T is a space of continuous characters of QP star, and it just turns out that every such continuous character is automatically locally analytic. Okay, so here I should say equivalently locally analytic. So that's kind of one remark I want to make, and then the second remark is that this space up here that I just wrote you down is nothing but a disjoint union of a bunch of open unit disks. Okay, so SPIF. This just decomposes as a disjoint union of SPIF ZPT, just a finite disjoint union of such, and that's just something that I maybe want to denote B circ, which is a rigid open unit disk. Okay, so at least this space up there can be made fairly explicit, even though I maybe yet didn't tell you why it can be made explicit like this. And I want to tell you what these maps are and what the other players involved are. So here I have my space like this, which is T divided by GM. And then it maps to something more mysterious. Which are these stacks, which turn out to be isomorphic in the case of GM. More generally, for any torus, this canonical map is an isomorphism. And this one here have a natural structure map to the affine line over A1. And over here, I can easily tell you what this map is. So if you have here a locally analytic character, what you want to do is you want to take the derivative of this character. Okay, and this will just then take values in the Lie algebra of GM of something, hence in GA of something, and hence give you a point of the affine line. Okay, and I yet didn't describe you what this object is, but this will be an object of fundamental interest later on. So for now, I just will tell you that this one is a non-trivial GM gerb over A1. Okay, to be described in more detail later on. But that's roughly the picture of these stacks in the case of GM. Okay.
Sorry, could you say again what the bottom map to A1 is?
I yet didn't tell you what this map is. I will define it. But I told you what's a composite made with, which is just taking the derivative. All right, so basically this map here is given by the Sen operator. But this will be introduced in a few moments, hopefully. All right. So in order to answer Dustin's questions, I should talk about the relation to Galois representations. And the variant. Well, he didn't ask about the latter, but still I will talk about it. And the variant for the RAM representations. Okay, so we call that if my coefficients A are just the p-adic numbers QP itself, so I'm doing it not in families, but the absolute case over a point, then I have a fully faithful embedding of continuous representations of the Galois group of QP on finite dimensional QP vector spaces. That admits a fully faithful embedding into the thing that I'm studying up there. Okay, so into Gal QP equivariant vector bundles over the Fark-Fontaine curve. Okay, and this embedding, in fact, is a very easy to write down thing. I take my representation V and I tensorize it up with a structure sheaf and equip this object with a diagonal action of the Galois group. Okay, so that makes it into a Galois equivariant vector bundle that becomes the trivial vector bundle after forgetting the Galois action. Okay, and this should already tell you that something interesting is true. That's something proven by Fark and Fontaine in their paper when they introduced the Fark-Fontaine curve, that the essential image of this functor consists exactly of those Galois equivariant vector bundles whose underlying vector bundle is trivial. Okay? But there are more. And so I should rather say something like in this sense. LS Fark-Fontaine GLN should be thought of as a generalization of the moduli stack of n-dimensional Galois representations. Continuous. Okay, so in fact it contains this stack appropriately defined as an open substack. But it is kind of way larger because in particular you allow yourself to see kind of vector bundles or families of vector bundles whose underlying vector bundle is not pointwise a trivial bundle. Like pointwise in the base parameterizing the families. Okay. And then I hope that from p-adic Hodge theory, you are familiar with the notion of Galois representations that are de Rham. So that's the property that a p-adic Galois representation can or can not have. So in here, I would have the functor or the subcategory of Gal QP representations that are de Rham. In the sense defined by Fontaine. Okay. And for them, there is a very nice description in terms of linear algebra, basically given by Fontaine's functors d quiz or d semi-stable, or then maybe in the potentially semi-stable case. So here I take V. I tensorize it up with the ring B semi-stable and take the invariance for the Galois group, but not over QP. This would be too strict, and I would lose a lot of interesting representations, but kind of just for the Galois group of some finite extension, and then taking the co-limit over all L over QP finite. Okay, and the gadget that you get here, this is a finite dimensional vector space over QP and ramified. Let's call it, I don't know, M. And it comes equipped with the action of the Galois group. And it comes equipped with the Frobenius and so this is a Frobenius linear automorphism. And this usual derivation n, such that n phi is p phi n. And these are both commuting with the Galois action. Okay. And then there was missing a filtration. Together with the Gal QP stable Z filtration on M base change to QP bar. So basically at each finite step, this gadget is supposed to be defined over the maximal anomorphic extension, L naught, inside of L, and the filtration is supposed to be defined after extending scalars to L. Okay, but I'm just writing this down after passing to the limit. And the gadget that you get is like what I guess it's called then that filtered phi n Gal QP modules. Okay, that's the category of objects like such that also embed via an explicit and fully faithful functor into equivariant vector bundles on the Fark-Fontaine curve. And in terms of classical p-adic Hodge theory, here you would describe the essential image of the functor as those set filtrations that are called admissible or weakly admissible, and well, which are the same. But when the notion was introduced, it was just a conjecture that they are the same. And this kind of is a semi-stability condition that exactly corresponds up there to asking that the underlying vector bundle of an equivariant vector bundle in fact is trivial.
I'm still confused. I'm hoping
Okay.
you unconfuse me.
I hope
So, so an example of something up there that's not in there would maybe be O of 1.
Yes.
Okay, and O of 1 in terms of this explication of the line bundle case, I guess that is supposed to correspond to like the representation which is trivial on ZP cross and sends maybe, or, well, tell me what it corresponds to.
Well, I mean, like, in terms of this isomorphism, it's kind of maybe less direct to see. Because, okay, let's say what is possible to say directly is what the kind of things correspond to whose underlying vector bundle is trivial. Namely, these are the unitary characters.
Whose underlying vector bundle is trivial. So
Right.
over a point, that's everything.
No. Like, it's kind of, over a point, you still have an equivariant line bundle on the Frank-Fontaine curve, which can or cannot be trivial. Right? It could be O of 1 equipped
the
with...
underlying vector bundle should be trivial, and it is.
Then maybe I didn't get the order of the question.
Oh, yes, right. So, no, my question was simply, we have a QP valued point of your stack, right?
Right.
Which is given by O of the vector bundle, Galois equivariant vector bundle O of 1 on the Frank-Fontaine curve.
Yes.
And now you've described your stack,
Yes.
and I want to know, in terms of this description, what is that?
Right. And I'm kind of first trying to answer the converse thing, namely how to recognize the characters such that the corresponding vector bundle, the underlying vector bundle, is the structure sheaf.
Right.
And these are exactly the unitary characters.
Unitary characters.
Right.
Understood.
And so, for example, if you just kind of want to map P to P, takes the anomified character, which is kind of the identity on P to the Z. This would correspond to, well, it's a character, but its underlying line bundle would be O of 1 or O of -1, depending whether I can get normalization straight.
Okay. But then there's actually something interesting happening here where... I mean,
I hope.
No, I mean because well...
Yeah, go on.
I mean, because it seemed over a point, it makes it look like you've got say all the usual Galois representations. Then you can tensor them with O of n for any n, and it looks like you've got a Z cross usual Galois representation thing. But when you go over to that picture, it's like the difference between QP cross representations and QP cross hat representations, like Galois versus Bay group. And there, it's not like it doesn't feel the same. So there must be something happening in families, even in the rank 1 case. Do you understand? This is not a precise question, so I don't mind you ignoring me and continuing.
Let's maybe discuss that later, because I would like to answer something, but this maybe would like to lead a little bit away from what I actually want to say. Okay, and so I hence want to be able to define the RAM variant of these stacks. Okay, as well, let me be a little bit sloppy and just say that I want to map some SPA A to a filtered phi n Gal module over a tensor QP anomified. Okay, so it's a Z filtered. What's the order? Mod projective module of rank n over a tensor QP unramified. And here my QP unramified is supposed to be not completed and the tensor product is not completed as you should think of it otherwise as this colimit, right? Okay. And for fixed lambda, say given by lambda 1 less or equal to, and so on, up to lambda n in z to the n, we then can make sense of the closed substack where the filtration is a filtration of type lambda or with weights lambda. Be the closed substack where the Z filtration is of type lambda. Okay, and then I want to tell you two things that going back to families, it is possible to say what kind of the effect of this functor or this embedding is, which tells you that this one here is exactly what the notation suggests. Namely, it's the closed substack of this stack of all equivalent vector bundles, where the vector bundle is the RAM of hot state rate lambda. In a sense, I didn't yet properly defined, but I want to use kind of maybe what you're familiar with from Pierre-de-Koch theory, so that and say that you hopefully maybe have a feeling what this is, and I will precisely define it next time. Yes?
Means what?
Well, that the lambda I counted with multiplicity are the jumps of the filtration. As usual.
Wouldn't this be locally closed?
No. Well, it will be locally closed, but it will also be closed. It's open and closed. Okay. It's both. It's a connected component. Let me say closed plus open. Okay. And that's a theorem which is, well, maybe just a formulation in this stacky picture of a result due to Berger and Colmes. They don't introduce these stacks, but they prove everything that you need in order to prove the theorem once you have introduced the stacks. That tells you that LS, and so I should say that the theorem means that the RAM is the same thing as potentially semi-stable in families. Okay, so even though I called this the RAM variant, by definition, these rather are the objects that are potentially semi-stable. I just, because of the theorem, don't want to distinguish the two names. Okay, and so the statement is that LS Farc-Fontaine GLN the RAM, comma lambda identifies is isomorphic to the closed substack of LS Farc-Fontaine GLN, where the equivariant vector bundles are semi-stable, are de Rham of Hodge-Tate weight lambda. And it certainly is part of the statement that this actually does define a closed substack, okay, which is maybe the kind of first thing to prove in this. All right.
Is it better notion defined pointwise?
Sorry?
The RAM is defined pointwise?
I will properly define what de Rham means using the stacks of BD1 plus representations and so on, as soon as I can in some sense come to more closely discussing their geometry. So in some sense it's another thing where I should put to be precisely defined next time.
And this is not open.
This is not open. This is proper close. So this one here has dimension 0, where this one here is supposed to have dimension n squared, for example. Yes.
So in the definition of LS de Rham, why do we look at projective modules over A times QP NR? Is it so that we get a stack, or for which reason do we tensor by QP and ramified?
Why I want to tensor with this guy here? Just because the data that I want to put in families live over that. So in some sense, whenever you specialize to a point of spar A, you should see something like this. And hence your object in some sense should live over A tensor QP and ramified. Okay. And yes?
Why is this reminds me? Why is the dimension 0 and not the 5 variety?
Oh, sorry, yes. Okay, I would have noticed this mistake after writing down the statement I wanted to write on that board. It's the dimension of the flag variety. Right. So, I mean, I want to precisely tell you what this is. So it's maybe a proposition. Okay, so when you study p-adic Hodge theory, you maybe are familiar with the passage from this kind of phi and Galois modules to Veil-Delin representations, okay, which is a construction due to Fontaine that in some sense tells you how to start with something like this and just produce a Veil-Delin representation. And this works in some sense once you have base changed your coefficients to QP unramified. Okay, so there in some sense you can get rid of this annoying semilinearity of the Frobenius by projecting maybe to one direct factor in a decomposition. Okay, and kind of elaborating on this just tells you what this stack looks like. So let me write this out as the following proposition. Over QP unramified, this stack LS Fontaine GLN de Rham and then Hodge-Tate weight lambda becomes isomorphic to the stack of Veil-Delin representations. And then I have to add some flag. Okay, so that's a stack of Veil-Delin representations of dimension n. So it's exactly what this X for the L group of GLN in Fark-Scholze looked like in the beginning. Okay, so from the beginning. So it really parameterizes Bell-Linear representations of dimension n. It lives canonically over point mod GLN. It parameterizes vector bundles with extra structure. And then here I have the flag variety of type lambda divided out by GLN. And I just have to take this product. And this kind of answers the question about the dimension. It's this guy here, which is supposed to have dimension 0. And then you see that kind of the stack of the one representation has dimension exactly equal to the dimension of the flag variety. All right. And I guess I want to end with coming back to the example of GM. Okay, where I recall that I had this guy here, which looked like T mod GM, and then I had the map down to A1, which basically looked like taking a character and mapping it to its derivative. Okay, and so here, let's call this the weight map, because it basically parameterizes Hodge state weights. Then this local systems de Rham, lambda. What's my notation? This one here is exactly the pre-image of the under the weight map of lambda seen as an integer, which hence kind of defines a point in A1. Okay, so in particular, if I take weight 0, I'm aware of this, but the only other option would be that I can't write. Hence, I will kind of lower it in a second. I refuse to bend in front of you. So, in particular, if I restrict to weight 0, then I get the smooth characters. And now I can lower the board again. Okay, so the de Rham locus of weight lambda is exactly those characters that have derivative lambda, which is an integer and hence a point in A1. And clearly, the kernel of this map, so the pre-image of 0, are those characters with derivative 0, which means that eventually, after restricting to some open neighborhood, they become constant, okay, which is a definition of smooth. Okay, hence you directly see that over there you parameterize smooth characters, which you should in some sense see in connection with this statement up there. Okay, so that, well, on the de Rham locus, in some sense, you see something which should be related to the smooth story. Okay, so the Bell-Linear representations of rank 1 obviously should parameterize the smooth characters in the kind of more classical Fark-Scholze picture. And I guess that should be it for today.
Thank you, Eugen. Are there any questions?
You had one.
I do. I have a question. But I'll give the others a chance first.
Could you maybe sketch how you go from characters to equivalent bundle on the field?
Yes. So the question was how to go from characters to equivalent vector bundles, and that's basically by local class field theory. So maybe I always something like so. Delta from QP star to let me do it just for a point, not in families, but the construction is just the very same. It's just in some sense for because I don't want to introduce some A. Then you have this kind of covering of the Fark-Fontaine curve, which was this thing that I actually wrote down in the beginning because I forgot to mod out by phi. Spar something like this. And then you just take, so. And then you want to divide out by phi to the z. And then, okay, so I have to try not to trick myself by doing this on the spot on the board. But what you want to do is you want to take the structure sheaf on the Fark-Fontaine curve and well, I mean, like basically you want to twist it by delta and descend it down here, okay? And you just have to make this in some sense carefully so that it makes sense. I guess it's maybe better to leave it like this before I write something extremely stupid on the blackboard. Like, yeah.
But just like if we enlarge the coefficients and had fractional powers of p, then we end up using these finite covers of the curve. And
say it again.
I suppose we took a delta with coefficients out
in some
yes, or just so we could take like a send p to a square root of p.
Why?
And then we would use the fractional covers if it was like some O over half, it's thought of as being rank 1 over a quadratic field.
I'm not sure whether I exactly understand. Like, is it a remark or a complaint?
Question looking for confirmation, but I mean it's just more because of Dustin's comment about twisting by integral powers of p. But
why?
When you extend the coefficients, you can have fractional powers of p. So that's kind of confirming that they come from fractional vector bundles, which thought of as rank 1 over some coefficient field.
So like. So in order to write something reasonable in here, let's say if it's a unitary character, then it extends to a character of the Galois group of QP just by local class field theory, and then you can kind of twist this pi delta and descend. And then in some sense you still have to worry what to do about the non-unitary characters. Okay, but kind of as everything can be written as a unitary character times something which is just a character of p to the z, you in some sense can add these by hand if you want.
But you already added some of them as unitary characters. This is what was confusing me. And somehow it's compatible. Well, anyway.
It is, but.
And how do you go in the other direction?
In the other direction, kind of coming from rank 1 things here to characters. Well, if it's an isomorphism, you obviously should. I guess I wouldn't be able to write down the functor on the spot, like in kind of a nice close form.
But for families, don't you have to use non-trivial?
Say it again?
For families, don't you have to use some non-trivial statements that you can always write them as they always come from a delta loop.
Right. Yeah, like you have to prove something, like which is kind of something obvious if I do it here, but with coefficients you have to prove a little bit. That's true. Yes. So I was maybe swiping a little bit under the wall.
Is there any reason why you didn't use Figma module all the way? I mean. No, I mean because
I have to give a joint course together with others.
but equivalently, could you descent everything and use Figma module?
Right, that's correct. Yes. Like this, the descent that you have kind of for objects over QP from Goldberg-Evane vector bundles to Figma modules with rubber wings. This just does work in families. Yes.
I have a question. So in your definition of specs, you are working with something like spec A cross the Fark-Fontaine curve, right?
Yes.
Is that different than taking the relative Fark-Fontaine curve over spec A?
Yes, that's very different, and that's in some sense a reason why I take this strange notation LS for my stacks, because I don't want to call them BAN in order to kind of emphasize this difference. So like Fark and Scholze define something like the relative Fark-Fontaine curve. Maybe a priori on perfected spaces of characteristic P, but then you can kind of bootstrap from there, maybe even to like to diamonds, and then also to widget spaces or semi-normal widget spaces or something like this. Which is a rather complicated construction, but it's definitely not what I'm doing here. I'm just taking the extremely simple product in adic spaces over QP of my widget space over QP with this kind of one version of the Fark-Fontaine curve attached to C. Like these are just two adic spaces over QP, one widget and one kind of slightly bigger, and it just takes the tensor product, the fiber product over QP as adic spaces, and that's it, and has, well, in some sense, nothing in common with the Fark-Scholze construction, except that kind of both deserve to be called some kind of family version of Fark-Fontaine curve, but of a rather different kind.
I mean, you're varying the coefficients and they're
right.
The geometry.
Right, exactly. So kind of if you want to compare this to Galois representations in some sense, I would take representations of Gal QP with coefficients in Tate algebras A, whereas kind of the Fark-Scholze picture rather would correspond to representations on QP vector spaces, but of fundamental groups.
If I could ask you a quick question.
Of course.
So if I'm not misunderstanding something, when you have one of these de Rham objects, you get not just a vector bundle, a Galois covariant vector bundle, but you get also a data to make a modification.
Right.
So is there any interest in introducing like the analog of LS, but where you have two vector bundles plus a modification?
Yes. And this will be of great importance in my second talk. And you might actually, let me just answer this by, that's exactly the reason why I introduced and wanted to talk about the stack of B2 plus representations. Yeah. Okay. Because this is in some sense exactly coming into play once you want to analyze modifications of a given vector bundle.
Okay. Okay. If there are no other questions, let's thank Eugen.